Welcome to problem 2-4. This is a really fun exercise, actually. The only problem with problem 2-4 is it's actually a camouflaged version of what we call mixture distributions that we're looking at in problem 2-4. And the curriculum starts on mixture distributions in chapter 4, which means essentially if you only have the contents from chapter 2, you're not theoretically equipped to do this problem. So the way we'll go through this exercise is we'll start by reading the text, and we will solve it using a kind of intuitive reasoning first. So that will be the first part. And then after we've done that, we will come back and try to read the section on mixture distributions in chapter 4 together and try to match the content of this problem with the terminology that we are equipped with in the mixture distribution section. So let's just start out by considering what this exercise is all about. So what do we have here? You are the happy owner of some uninsured property in the Caribbean. So you're a happy owner of uninsured property. Don't know how well those two things go together if it's in the Caribbean, but anywho's, a tropical storm is approaching. And instead of running for your life, you decide to try and calculate some things about the distribution of your loss and the expected value of how big the loss will be when the storm hits. So what do they say here? Rescaling the measurement of storms, we say that it will be of strength 1, 2, or 3. And the following probabilities are also known. So the probability that the storm is of strength I is given by Pi, for I equals 1, 2, 3. So what does that mean? Well, that means the probability that the storm has strength 1 is given by some number P1, so that's given by some probability. And the probability that the storm has strength 2 is given by another probability, P2. And there's probability P3 that the storm will be of strength 3. And then they say, in particular, if you add up these three probabilities, P1, P2, P3, they will equal 1 altogether. So the storm will have either strength 1 or 2 or 3, and there are no other possibilities. So given that the storm is of strength I, your loss will be exponentially distributed with parameter lambda I. And let X be your total loss, i.e. the unconditional loss. So how should we read this? Well, the way we should read this is, given our storm has strength 1, so given storm strength 1, X will be exponentially distributed with parameter lambda 1. And given the storm has strength 2, the loss X will be exponentially distributed with parameter lambda 2. And given our storm has strength 3, x will be exponentially distributed with parameter lambda 3. So what does this mean? Well, this means the loss, the amount of damage done to your property in the Caribbean depends on the strength of the storm. So if the storm has a smaller strength, then we expect the loss to be smaller. So we will then say then the loss will be distributed with another parameter exponentially than if the storm had another strength, for example. Now this is only vaguely confusing intuitively because, well, it kind of makes sense, right? Because if the storm has strength 1 compared to strength 3, then probably if the storm is of strength 1, we only expect some windows to get blown up off the house. But if the storm has strength 3, we maybe expect flooding and the whole house just to collapse and just float away or something like that. But however, even though we know the strength of the storm, we can't say then X will be 100,000 or something, because even if we know the strength of the storm, the exact damages on the house can also vary, just depending on your luck, right? So that is why even given storm strength, then the loss will be exponentially distributed with some parameter. Now, just before we go on to doing the exercises here, they also give us a little hint. They say if we have some stochastic variable that is exponentially distributed with parameter lambda, well, then it has this density here, and it has this mean value and this variance. So what can we see from this? Well, we see that the bigger the lambda parameter is, the smaller is the expected value. So the bigger the lambda parameter is, the smaller the expected value of our total loss will be, which kind of, just, even though this isn't relevant for the exercise, but if we just think a little bit about it, it would make sense if we had a bigger value of lambda here and a smaller value of lambda here, because that would mean we have a lower expected value of damage here and a higher expected value of damage with the higher strength of storm. So this is what the exercise is about. Just before we end this, I want to kind of put all of this down here in quotation marks, because, well, X has one distribution. It doesn't have 3 distributions, but it's just given different values of storm strength. The conditional distribution of X will be different. So this is not the absolute distribution of X. It's the conditional distribution of X given storm strength 1 in the first case, and the conditional distribution of X given storm strength 2, and so on and so on. So in the next video, we will solve A, B, and C intuitively, and afterwards we will take a look at mixture distributions and tackle this in a more formalistic way.